just need to have faith. Keep me from keeping me down. Even me out. Free me, so I'm not afraid. Gotta let it go. Let it flutter. Let it flutter. Gotta let it go. Let it flutter. Let it flutter. I'm over catching butterflies. Let it flutter. Let it flutter. I'm over catching So what if I make a fool? My ego can only bruise. It's nothing that I can't take. It's better than being numb, waiting for sleep to come, so I can dream about change. Gotta let it go. Let it flutter. Let it flutter. Gotta let it go. Let it flutter. Let it flutter. I'm over catching butterflies. I'm over catching butterflies. Let it flutter. Let it flutter. Gotta let it go. Let it flutter. Let it flutter. Gotta let it go. Let it flutter. Let it flutter. I'm over catching butterflies. Let it flutter. Let it flutter. I'm over catching Let it flutter. Let it flutter.
All right, good morning, everybody. Just getting stuff last minute set up and switching scenes now. All right. So we're going to be, sorry, I need to talk into the microphone. So today we're going to be talking about life history. We had talked about this a little bit before. So it's my, what it is, 600. There we go. Life history, right? And this life history, we're talking about this in the point of ecology, not necessarily in kind of what everything has happened over a lifetime. So when we refer to this, we're thinking about basic demographic information of a population or a species. So the stuff that appeared in that life table that we covered last time. So it includes when organisms first reproduce, how many offspring they have in each round of reproduction, how many times reproduction occurs, their total lifespan, all of that stuff. So for example, if we're going to use humans, life history involves a late start to reproduction. So given no societal bounds, reproduction would start around 14, 15 years old. You'd have very few offspring, but you are able to reproduce multiple times up until you hit around 45 to 50 years old, and then reproduction stops. So that's what we mean by life history. So it has to do with two components. So the first one is survival, and the second one is reproduction. So survival and reproduction. These two things kind of play into it, because remember that if you die, your fitness drops to 0. All right. So if you die, your fitness essentially drops to 0. And so what we do instead is we talk about kind of these life history strategies as they pertain to the average organism. So it's shaped by natural selection. It represents how many species or how many members of a species distribute resources, growth, survival, and then the production of those offspring, and then what happens to those offspring. So remember that everything alive needs energy and nutrients. All right, energy and nutrients. Why? Well, because energy is what we turn into biomass and what we use as movement, and nutrients help supplement all of that stuff. Without that, we're unable to grow, we're unable to maintain ourselves, and then we're also unable to reproduce. So you have to think that in nature, for the average organism, all right, that resources are going to be limited, and then there's competition for those. So one of the things that we always talk about, it's like, oh, well, how do plants compete for resources? Well, if you go into a forest, one of the things that you'll notice is that there's very little grass on the forest floor. Why? Well, because it's difficult for sunlight to kind of reach down to that, because trees are so tall. Trees have learned to outcompete other plants for light, which is a basic resource. And as trees die and fall, they open up spots in the canopy where light can come through, and then other organisms can take that spot. The other thing is plants with deeper roots, or that form kind of these like more stringy roots, can kind of get access to minerals that might not be available. So each organism basically has a non-infinite amount of resources, and it has to divide that up between growth, maintenance, and reproduction. All right. Most people that are in high school are kind of near the end of their growth cycle. I know there's some of you that statement disappoints you a little bit, but for the most part, a lot of you are kind of done growing. So then you have to, why do we still eat if we're not growing? Well, we're going to need to maintain that. All right, we're going to need to maintain our bodies, and that is because, you know, whenever we go for a walk, or we go running, or we work out, you could feel the soreness in your muscles. We have to rebuild that stuff. Basic activities that you do, you know, that uses energy. You have to be able to supply that. You have to be able to repair tissue that's damaged through day-to-day activities. And then on top of that, when you get old enough and get to the point where you're going to start having children, you have to be able to supply for that reproduction. So from an evolutionary standpoint, these resources have to be kind of allocated, and they're not allocated easily, and that's where we come up with the term fitness. And fitness is the number of offspring an organism leaves in the next generation, because it is kind of assumed that if an organism has high fitness, it's also going to be reproducing more. All right. And so don't think of this as physical fitness. Think of this as a measure of how many offspring an organism has. So if you look at myself, my fitness is 0 because I have no children. But then you look at other teachers in the building that have, you know, 3, 4, 5 children, then their fitness is obviously a lot higher than mine. And so does that say anything about their physical fitness, like the ability to physically compete in, like, let's say a running race or a triathlon or anything like that? No, it doesn't say anything about that. What it says instead is it bears to how many children they were able to have. So organisms with inherent traits to cause them to distribute the resources more effectively and to do better in that growth, maintenance, and reproduction end up having a higher fitness, and therefore they have a greater chance through variation to make it through natural selection. And over long periods of time, we look at this and we call this life history strategies. And life history strategies, so life history, and then we're just going to add in strategies down here at the bottom. So strategies is just a way of saying a collection of life history traits. All right. And those life history traits can be offspring timing, number of offspring, the amount of parental care, age length. All of these different things kind of play into it. And you can make those life history charts that we saw on Monday, you could make those based off of this information. You have to observe enough organisms. You know, if you observe myself, you'd be like, wow, this guy is has really poor fitness because he has no children. So the life history of this species has to be bad. Well, no, not necessarily, because that's just looking at one organism. You know, you have to look at multiple organisms. So in this, we're going to look at some of the trade-offs in life history strategies, and we're going to look at it from plants and animals. All right. Again, if you have any comments or any questions, type them into the chat and I'll answer them. Okay, so one major trade-off that you have to have is the number of offspring and parental investment in that offspring. All right, so this is the kind of the quantity versus quality argument that we've talked about. Humans have one offspring, one kid at a time. I know there's exceptions with people that have twins and so on, but usually one organism at a time. And there's a lot of parental care that goes into that. Compare that to a mosquito, where a mosquito lays hundreds or more eggs and has no parental care. It lays those eggs and then good luck. Hopefully they make it. And so we have to be able to put a quantity on that, right? So what we do is we call that fecundity. FECUNDITY. You know, now that we only have a week of class left, it's one of those things that I wish I had the little writing tablet, but I'm not going to buy one now because by the time I get it in, it's going to be over. Okay, so fecundity, this is the amount of energy. The worst R ever written. The amount of energy invested per offspring. All right, the amount of energy invested per offspring. Almost messed up spelling that, but I got it. Okay, the amount of energy invested per offspring. So the higher the fecundity, the less energy, and this is inverse. All right, so this is inverse. And what I mean by inverse is as the amount goes up, that means you're actually investing less energy. So having a high amount of energy invested per organism gives you a lower fecundity. So the higher the fecundity, the less energy is likely to be invested in each organism, both in terms of resources and fuel reserve placed in eggs or seeds. So you could think of an apple. So with an apple, you have this kind of like apple shape here, and you got the core. I guess I should have done it in red. And then on the inside of that, you have these seeds that are in the center, right? This entire red space is energy is a reward with energy being contained within each of those seeds. All right. So that is how we kind of talk about that, like the energy reserves and things like that. So organisms that produce a large number of offspring tend to make a relatively small energy investment in each individual. So they don't provide much parental care. When the seeds kind of leave, when the eggs are laid, all of that stuff, the organism's kind of on its own, hoping that some are going to survive. If you have 1,000 eggs, you lay 1,000 eggs and 1% survives, that's still 10 that make it. And so a lot of that is just hoping that some of them will make it. Organisms that have few offspring usually make large investments into each of them and provide a lot of parental care. And they're really good at kind of putting all their eggs in one basket. And they invest heavily into the survival of each of those organisms. And again, this is a general trend. It's not universal. There are exceptions to this. So for example, I just thought of an example and I forgot it. Either way, there are exceptions to this. where there is kind of low investment and things like that. But with each of these, you know, you can kind of see the trade-off. Like you have one kid, and if that kid doesn't make it, that is a lot of, I guess, like wasted time investing and energy investing in that, compared to with an organism that has, you know, thousands of eggs. There's a lot of wasted energy that went into producing a ton of eggs just for a small handful to survive. But some of them do survive, which means in the end it was a success. As long as there's one organism to replace the original, then I guess it can be considered a success. Compare that to humans, though. It does sound kind of mean, but like if you have a kid and it doesn't make it, then that's a big kind of energy and resource and time investment that's been put into that for it to not work. I know it sounds really mean, but think of that as in like a wild animal state. So let's use an example. I have a folder that has some pictures in it. Let's look at these eggs. So this is a sea snail called a whelk, W-H-E-L-K, and they produce hundreds of eggs in one spot. And all of these eggs will hatch to yield a little baby snail, and they're pretty self-sufficient from the get-go. So here's all those, a cluster of those eggs. But here's the issue. The first 10% of the eggs that hatch usually end up eating the rest of the eggs. All right, so this is an illustration of a parental investment strategy. So the sea snails and other marine invertebrates being insects and things like that. So marine invertebrates, they provide little or no care to their offspring. Instead, what they do is they have an energy budget to make a lot of offspring, and then out of that, a relatively small amount are going to make it. So even though, yes, this looks like a lot of eggs, you know, if 10% make it, so let's say there's 100 eggs here, 10% make it, those 10% are going to start to consume the other 90%. But the sea snail, I mean, you have to think that, okay, yes, that's a sea snail, but then you look at something like a sea urchin that can release up to 100,000 or 100 million eggs in a single spawning cycle. And again, very, very few of those are actually going to make it. So instead of investing its energy to just caring for, like, let's say this one individual right here, it invests its energy into producing millions of these eggs to go out there and hopefully make it. So that's one type of strategy. In this, the offspring has to be self-sufficient from an early age. So compare that again to our other example, humans, where humans are pretty useless until they hit around like 5 years old. And once they hit 5 years old, yeah, they're still pretty useless, but they're a little bit more self-sufficient at that point. Like you can kind of give them tasks and things like that to do. While I can tell a 5-year-old like, hey, can you run and throw this in the sink for me? While with a 2-year-old, if I try to do the same thing, then that would not end up well. So they tend to have very little energy invested in the individual, but a fair bit invested in the whole chunk, and they tend to be small and you have low energy reserves, but they're extremely vulnerable. Many won't survive, and it's just a sheer numbers sort of thing. You know, it's back when I used to play StarCraft, we always used to make the joke that it's like, you know, yes, rock beats scissors, but do you know what else and then scissors beats paper and paper beats rock, but do you know what else beats paper? A lot of rocks. And so if you have a lot that are disadvantaged, some of them will eventually make it. So using sheer numbers. All right. And then the other example in this that I want to give is a newborn panda. So here's a newborn panda. So these kind of have the opposite strategy. Panda females have one cub at a time, and they are far from self-sufficient. I mean, look at this thing. It's extremely small. It's probably about the size of like a full-grown mouse, right? And because of this, there's very, very few, and the mom will invest a lot into this offspring. There's a video online of a panda who had twins, and if a panda has twins, she'll completely ignore one of them because she only cares for one. So what they do in order to nurse that other one is they actually switch them out, and the mother has a really difficult time in telling the difference. But one at a time. So they have very, very few reproductive events, and because of that, they put a lot of care into this offspring. And it might look tiny, but it's actually like decently sized. Like I said, it's about the size of like a full grown mouse. And what they do is that the female panda, or the mother, will put a lot of investment into this one organism to make sure that it stays healthy, and that comes out of its energy budget. So remember, in your energy budget, going back to paint, you have these life history traits, right? And so the life history traits, or the energy, has to go to build, maintain, and reproduce. All right, build, maintain, reproduce. Energy was used in reproducing, but it's not just the physical act of reproduction or having an offspring or producing an offspring, it's also caring for it. So the care for this, the panda has to budget all of this stuff, because it just can't say, oh, I'm reproducing right now, so I don't need to maintain. No, it still has to maintain. And if you've seen pandas are pretty stupid and they get hurt all the time. So it also has to rebuild tissue and then maintain those tissues, and then again invest into this tiny offspring, because it's not really going to make it. And this tends to be a pretty common strategy for mammals. So humans, pandas, a lot of the apes, they're relatively helpless at birth, and they need a lot of help in order to develop to the point where they become self-sufficient. All right. And so I have another picture. Here's a full-grown panda, in case no one has ever seen a panda before. But this is a full-grown panda. So you can see that the full-grown panda is a lot better at kind of developing, or in order to forage and things like that. And so it has to have or invest quite a bit in order to get this panda cub up to full size. If you want to see one of the funniest videos in the world, look up panda sneeze, and it's this little baby panda that sneezes, and it's so loud it scares the crap out of its mom. It's hilarious. It was like real early 2000, or like 2008, 2009 viral video. And a lot of this stuff, kind of back on track, a lot of this stuff kind of applies to plants too. Plants aren't really providing a whole lot of parental care in the same way they do with their animals, or the same way animals do. But instead what they do is you could produce cheap seeds, or you could produce expensive seeds. So what's the difference? So look at a plant like a coconut, right? The major part of a coconut is energy, and chestnuts too, and there's other ones. They put a ton of energy into the fruit, and the fruit is a dispersal mechanism for the seed. So it puts a lot of energy investment into that fruit in order to make sure that the seed makes it. Compare that to something like grass, where it's just really cheap seeds. So like orchids are the same way. You just give off a ton of really poor quality seeds and hope that some of them make it. Instead, the parent plant has to dump a lot of energy into making a coconut compared to, making a grass seed. Same thing with like an apple. Again, if you guys have any questions, post them into chat and I'll answer them. So then you have timing of first reproduction. I should do another paint window. Paint. So timing of first reproduction. So this can be either early, and then that's going to be versus late. All right, and there's benefits and detriments for each of them. So there are pros and cons. So organisms that reproduce early have a risk of leaving no offsprings at all, and it's still expensive for growth and health. So you have to think of like small fish, like guppies. They use a lot of energy to reproduce. So they throw a ton of energy into reproduction, but again, that is energy that they don't have for growth. But then you look at organisms that reproduce late, you have to survive to make it to that late stage. So if they reduce later, they have a greater fecundity or are able to provide better parental care. So on the flip side of that, they run a greater risk of not surviving to that reproductive age. So think about a bluegill or a shark, right? They use a lot of their energy in the growth. So going back to things needed, you need to build, maintain, and reproduce. So for a early organism, building there's not much going on there. So there's not a whole lot as far as building. Same thing with maintaining, but they have a lot in terms of reproduction compared to late, where you put a lot into building, a lot into maintaining, but you can save a little in reproduction compared to the overall span of all that stuff. So a lot of it is that if you delay reproduction, you can actually end up dying before having reproduction. So in general, the age of first reproduction is usually linked to the lifespan of a species. Short-lived species that reproduce really early tend to not live very long, while species that reproduce later in life tend to live for quite a while. All right. Now we're going to get into kind of some terms. Another one that we need to talk about is how many times does an organism reproduce over its lifespan? How many times is an organism going to reproduce? And for some, you only have one, and for others, you have multiple reproduction events. So we're going to start off with one, and this is called semelparity. All right, semelparity. And this is one reproductive event. So one reproductive event. This is where they only reproduce one time in their lifespan. After that reproduction event happens, usually they're on their way to death. They use up most of their resource budget. So again, their resource budget being build, maintain, reproduce. They use up most of it during this one event. So an example is bamboo. If you see a bamboo flower, it's most likely it's not going to make it. Another example is, where's my picture? Please tell me I saved this picture. I did. I can't spell. This is a Chinook salmon. So it's like the helicopter, but the salmon doesn't fly, it swims. And so this salmon uses up a lot of its energy reserves fighting to go from the ocean to a freshwater nesting area. Once it gets there, it reproduces, and then this thing dies. All right. So it uses a ton of its energy in this kind of build up to the reproduction. So it builds, maintains to become a big organism that's strong. Then after that, it spends its energy to swim to a reproductive site. And then after it has its reproductive event, then it's dead. And so it's a big trade-off there, because what if it fails? Then you've instantly spent all of that energy and you have nothing left, and that's it. So then this organism's fitness reduces to zero. The other trade-off of that is heteroparity. And this is multiple reproductive events. You ever watch on Twitch, you watch a streamer who's like really entertaining, but he's really bad at video games, and it's like painful just to watch him struggle through playing video games just really poorly, or like someone picks up a new game and they're literally a potato in it. I feel like that's what it's like watching me trying to write these letters out. It's just, it has to be like the most potato thing. Okay, so idioparity individuals reproduce repeated times on their lifetimes, and they kind of take different forms when they do that depending on the reproductive cycles. So they don't put everything into reproductive benefits, because for it, the fitness benefit is surviving to reproduce more times, and because of that you can have fewer offspring and invest in them. So some animals can only mate once a year but then survive multiple seasons. So an example of that is this pronghorn antelope. All right, this is a pronghorn antelope. You could tell because of the way it is. These things, they go through what are called seasonal estrus cycles. You hear a lot of people, when they refer to like cats, you hear them call it heat. And this is hormone induced, and it's physiological. So it prepares their bodies for mating. And females of the species with estrus cycles mate only when males are going through the estrus cycle as well. So there has to be that temporal lining up of it. That right there goes back into our reproductive isolation, because if the males are not in heat of a different species, then females won't mate. So it kind of changes how a lot of that functions. So this is also observed in primates. Okay, I do have a picture. It's also observed in primates. So this is a chimpanzee. Chimpanzees also go through the same exact thing. So they might, so a different pattern is observed in primates, which attempts to kind of put, it limits the reproductive abilities. So the big one is menstrual cycles, and yes, chimpanzees go through that, and that only makes pregnancy likely for a few days each month. And what that does is it makes sure that, energy stocks are good and everything is fine. All of this other stuff of build, maintain is good to go. And then all of a sudden it just dumps into reproduction. So that's a little bit different when you look at chimpanzees. So I know that for some of you, that's a little bit too much information and you just learned something today that you really didn't want to learn. But, this is common, this is a common life history strategy for animals that are have heteroparity. There's like the world's loudest bird outside of my window, just screaming its face off right now. Okay, so again, I think that's going to be it for today. I did cover a fair bit. So we only have, so next week school is out on Thursday, so I'm going to do lesson for this on Monday, Wednesday. The homework, I'm going to have everything posted on Monday. If you have late work, if you have anything like that, you have until until Thursday to get it to me. All right, that's not Thursday at midnight. That's Thursday at about 5 o'clock. I'm going to put a cutoff on it. If you send me work after that, most likely it won't end up in the grade book, because I don't know what our plan of action is for next Friday. Everyone should have gotten an email and an auto dialer about, let me switch over to the camera. Everyone should have gotten an auto dialer and an email about locker clean out. Make sure you find out what your day is for locker clean out so that you can make it into the school for that. Is there anything else that I'm missing? Let me check my notes. I think that is everything. Just make sure that you're getting everything set up so that you can go in and clean out your locker. Now, going in and cleaning out your locker is going in and cleaning out your locker. It's not going in to hang out with your friends and all that stuff. You're going to be expected to kind of follow the directions, because, just because, some guy with that has 5 guns on him goes down to the state house and says COVID-19 is not a real thing and it's caused by 5G, doesn't mean that instantly the crisis is all clear. All right. We still have to follow procedures. Parents are going to have to wait out in the cars and things like that. But just be prepared that there's going to be kind of some restrictions on when you go in to clear out your locker. Make sure you bring in something to carry all your stuff out. Any textbooks, library books, anything that you have that belongs to the school, bring those in and turn those back in. If not, they'll probably charge you for it. We haven't heard any official word yet, so I really don't know. But most likely that's what's going to happen. What else? Make sure that you're getting homework turned in on time. If you have any questions, let me know. I'm going to go over to Google Meets after this so we can chat and you can ask any questions. Probably next week what I'll do is I'll just post a test, like a final test. And that way it's something you guys can kind of do, and it'll take, a class period to do it, and then get that turned in, and then that'll count as kind of your final grade for the semester. But last week is it. I know it's been kind of a weird semester, and we'll talk about that next week on Thursday. But that will be everything. There's my button. So have a good day. Stay safe. Work on anything you need to. Pay attention to your email and the auto dialers, and that'll be it.